Okay, um, let's get started. I think people will trickle in. Good morning, everyone. Not everyone, I guess, but good morning to many of you. um, it's okay. So Ashoke is going to give his third lecture on black holes and string theory.
Thank you. Okay, is my screen visible?
It is, yes.
Thank you. Okay, so let me begin by stating what we derived yesterday, okay, or what we argued yesterday. Okay. So we are doing the counting of a specific system that we argued will eventually become a black hole at strong enough coupling. And we also argued that we can think of that system as a collection of three independent systems. We have three independent systems. So the first is we have Q1 plus 1, D1 branes moving inside a D5. Then you have the motion of the D1, D5 system inside tau naught or KK. Okay, there's the same. And the third one is the dynamics of the Collinson-Klein monopole itself. Okay. And we define the partition function, which is a function of rho, sigma, and V. Here, n is the momentum along S1. So let me write this. This is momentum along S1. And the J is momentum along S1 tilde. This -1 to the J I have just included for convenience, but of course it makes no difference because this is, you could have eliminated this and then the corresponding partition function will just involve a shift of V by half. Okay, so this is just a matter of convenience and we'll see that it will be useful later. And what he argued is that this quantity will be given by a product of these three partition functions. So the first one I'll call ZD1. Then the second one is the center of mass motion, center of mass degrees of freedom motion inside the tau naught. And then the final one is ZKK. Okay. And now let me just state one thing, and that I'll not come back to this later. Okay. That when you do the counting, in carrying out the counting, we factor out the super multiplet generated by the Q alpha action, okay, which we saw yesterday. Okay, you get this 2 to the 6 dimensional multiplet, and these Q alphas essentially for this system appear as some kind of fermion zero modes. Okay. And these 2H to the 6, etc., they get absorbed in taking out the trace. And so we'll not discuss those fermion zero modes anymore in this counting. Okay. So what we'll see, for example, when you'll not see this 2H to the 6 factor anymore because they have gone into this fermion zero mode trace. Okay. But you will see a factor of -1 to the 2H, because as you saw that even after factoring out the zero mode the Q alpha contributions, you are left to this -1 to the 2S factor, okay, which is the S, that S refers to the one of the states in the super multiplet, okay, the state that is annihilated by all the QMs. Okay. So this is what you should keep in mind. So you'll not so when you calculate the trace, you will see -1 to the 2H appearing, but you will not see the 2H to the 6 factor appearing. That's because it has basically gone away after while tracing over this fermion zero modes. There is one more point that I should mention here, okay, and that in fact I had discussed yesterday, but let me state it again because it's important. So at the center of tau naught, we have approximate SO4 symmetry, because we saw that the metric looks like flat 4-dimensional metric at the center of the Karuzi-Klein monopole. And the SO4, of course, as at the level of the algebra, is isomorphic to the product of two SU2s. Okay, let me call this SU2 prime. Okay. So one of these, okay, let's say SU2 prime, this becomes the rotation group in 3+1 dimension. Okay, that's the action on the r theta phi part. Okay. This one is not an exact symmetry. Okay, this is broken to U1 in the full solution. Okay. And this gives the momentum along S1 tilde. Okay, we saw this yesterday. Okay. So one of the consequences of this is that the 4D angular momentum, okay, if you place an object at the center of tau naught, then the 4D angular momentum has information both about J and H. Okay. Remember, J is the momentum along S1 tilde. Okay, so that's some component of the 4D angular momentum. And H was the third component of the usual angular momentum. Okay, this rotation group. So that also has its origin in the SO4 angular momentum. Okay, so the 4D angular momentum contains both. Okay. And so if you have a particle that carries this 4D angular momentum, you have to be a little careful in analyzing whether it represents J or H or both. So this is something we should keep in mind. Okay, so we begin with the first system.
Just to clarify, we haven't, where did we use that we are doing this calculation in weakly coupled string theory?
Oh, because we are, I mean, we have already assumed that in some sense, because we are saying that this is the product structure, right? So this product structure will appear only in a weakly coupled string theory, right? Otherwise, there is coupling between these degrees of freedom. It's only in the weak string coupling that these degrees of freedom decouple.
Okay, thanks.
And then in various analysis, we will basically use the fact that the degrees of freedom are just free fields. And each of these of course, use the fact that you are using weakly coupled string theory. Okay, most of the calculation, in fact, all of the calculation will be done for free fields. Okay, as we'll see. Well, maybe not all, but most of it. Okay, so what is the first system? Q1 plus 1 D1 brains moving inside D5. And we wanted to carry some momentum along S1, carry momentum in along S1. We are actually calculating the partition function, not really the number of states, but they are related. Okay, we'll calculate the partition function for this system. So we'll sum over Q1 and N weighted by appropriate factors. But let's look at the simplest case. So simplest case is no D1 brain. Okay, that's Q1 equal to -1. Okay, means no D1 brain. Okay. And here, of course, there's nothing to count. Okay, only the ground state of D5 remains. Now, let me remind you that D5 itself, of course, has its own oscillations, but those go into the system too, right? The overall motion of the D1, D5 system in the Kaluza-Klein monopole in the tau knot space, that goes into system 2. Okay, so here in the system 1, we just have the ground state of D5 remaining, so nothing to count. So the first non-trivial case is really Q1 equal to 0. Yes, is Q1 equal to 0. Okay, that's a single D1 brain. So let me try to draw this. Okay, so we have, let's say this is the D5. And we have, this is the S1 direction because D5 wraps S1, and I'll denote the whole of K3 by 1 direction. That's the K3 direction. And the string that you are talking about, the D1 brain, okay, that's stuck on D5, so it cannot come out of the plane, okay, but it oscillates here. Okay. And these 2 points, of course, have to be identified, so it should begin and end at the same point, right? There is periodic identification along this end. So you should really think of this as a string wound around a circle. So you see that this D1 vibrates basically along the K3. Okay, so there is oscillation along K3. So D1 oscillates along K3. And these oscillations can carry momentum along S1, of course. And that's what you want to count. Now, how many such states are there? Okay. Now, there are also fermionic oscillators, okay, because D1 brain world volume has both bosonic and fermionic degrees of freedom. So, fermionic oscillators they carry spin, angular momentum, and these could appear as can contribute to J, S1 tilde momentum. So this is really like a supersymmetric 1 plus 1 dimensional supersymmetric sigma model, okay, whose target space is K3, right? Why 1 plus 1 dimensional? Because there is this S1 direction. It's you can think of it 1 dimensional. Okay? It's moving. The other dimension, of course, is time, and it's moving in K3, right? Because D5 brain is wrapping K3. So it's like a 1 plus 1 dimensional sigma model with target space K3. And that's a well-studied system. So we are going to use some of the results of that system. So
I have a
let's,
quick question.
yes, go ahead, please.
Could there be higher winding modes as well?
Well, here you remember Q1 is just 1, right? So only one winding.
I see.
For Q1 equal to 2, there will be higher winding mode, certainly.
Okay.
Yeah.
Maybe this is clear, but how much supersymmetry is there on the 1 plus 1D sigma model?
In this case, it's basically, it breaks all the supersymmetry. So let me see, I think it's 2 supersymmetric sigma model.
Okay,
From the point,
sure.
we have 1 plus 1 there. Okay, I'll try to clarify it later. Okay.
Sure, yeah.
Yeah. Okay.
Thank you.
Or yeah. Okay. Okay. So let's say NNJ. This we define as the number of states of this system with S1 momentum N, S1 tilde momentum, or maybe say angular momentum. Okay, I'll call it S1 tilde momentum, but of course, here it appears as and the particular component of the angular momentum, J. And you weight it by -1 to the power 2h plus j. -1 to the 2h because you are calculating the index, and -1 to the j because that's included in the definition of the partition function. Okay. So this quantity, okay, if you consider e to the power 2 pi I n sigma plus jv. Okay. This in fact is a well-known quantity. This is what is called the elliptic genus of K3.
Sorry, this T1 brain is not along S1 tilde. So why is S1 tilde relevant here?
Oh, because it carries angular momentum, right? This is what I had said earlier. It's not here. It's not appearing as S1 tilde momentum. It's appearing as the angular momentum that is carried by these fermionic oscillators. But I'm just calling this S1 tilde momentum because eventually it will become S1 tilde momentum.
I see. Okay, thanks.
Because angular momentum at the center of tau naught, right, is the actual momentum along S1 tilde. That's what you saw yesterday, right? The rotation, the one particular component of rotation at the center actually translates this coordinate psi, right, which is the coordinate along S1 tilde.
Right. Yes.
So that's the way the S1 tilde momentum appears.
Hi, another quick question. Where does H appear in this system?
Where does H appear? Yeah, H is also part of the angular momentum. Right? SO4
The angular momentum along S1 tilde.
Pardon?
The angular momentum along S1 tilde?
No. Okay. So SO4, let me go back. See, SO4 has two SU2s. One of these corresponds to H, has H information. Okay, because it's rotation group in 3 plus 1 dimension. The other one has the information about the S1 tilde momentum. So you have to look at a given fermionic oscillator, see which SU2 quantum numbers it's carrying, and this may either give H or it may give the J.
Okay, thank you.
Is that point clear? Right? Because
Yeah.
the fermions are spinors of SO4, right? So they can carry, depending on what kind of spinor it is, they can carry either this quantum number or that quantum number, and that's what you have to keep track of when you do the counting.
Okay, so the exponent on the -1, it's 2h plus j, not 2n plus j, right?
Yeah, 2h
Okay.
plus. Yes. Sorry, did I get it? Yeah,
No, no,
this is
you wrote it right. I wasn't sure.
yeah, it's 2H plus J. Okay, this is what decides whether it's fermionic or bosonic.
And the SO4 symmetry, is that that's the R symmetry of the sigma model? Is that right?
Yeah, exactly.
Yeah, okay.
That's like the R symmetry of the sigma model. Okay, so this quantity is known. Okay, I'll write down the answer for this. There are various ways of calculating this, but I mean, I think the most straightforward way is that because it's topological, you can go to the orbifold limit of K3 and just use the standard orbifold technique to calculate the spectrum, and from there you can calculate this. But the result for this is given by this quantity. So where these are just Jacobi theta functions. Okay, the three classical Jacobi theta functions. Okay, this is the argument is 0, this is the argument is v. This has also nice modular properties. Okay, modular and periodicity properties, and that makes it what is called a Jacobi form. Okay, so this is in fact a weak Jacobi form. Okay. And so this has an expansion of the following kind: C 4n minus j square e to the power 2 pi I n sigma plus jv. Okay, and these coefficients are known. Well, of course, these are standard functions, so the expansion coefficients are known, so you can just put it on a computer and find what these numbers are. Okay. But what is important is that this is actually a function of only this combination, 4n minus j square. Okay. And so this tells us that this counting now is done. Nj is C of 4n minus j square. Okay, so this is a simple case, but that's the counting. Okay. And in fact, we'll see that the final answer, okay, the only ingredient that the final answer needs is this one. Okay, other questions?
Yeah, earlier you said that we are going to compute the partition function, not the states, because it's easier to compute partition function. Is it because it factorizes, whereas the number of states won't factorize?
The partition function factorizes, number of states won't.
Okay.
So we'll use this to eventually construct the partition function, and then we'll take the product. Okay, so now let's go to the case of 2 Q1 equal to 1. That means 2 D1 branes. So let me draw the figure again. Okay, there are in fact two kinds of configurations that you can have. Okay, let me draw the first one. This is S1, this is K3. So one is just two separate D1 branes. Okay, each oscillating in its own way. So this system, okay, you can think of in the weak coupling limit, these are free. Okay, it's like free particles. Okay. You can just think of this as a case of two identical particles. Two identical particles. Each with many quantum states. Okay. So these quantum states are labeled by N and J, and the degeneracy is C 4n minus j square. Okay. And if C is positive, then it's a boson. If C is negative, it's a fermion. Okay. So this is standard statistical mechanics problem, right? The free ideal Bose gas or ideal Fermi gas. The only difference is that the individual bosons and fermions can exist in many quantum states. So this problem is easily solved, and I'll just write down the answer. It's basically just ideal gas problem. Okay, in fact, the partition function, of course, is the simplest thing to calculate. Okay? But in the case of 2, you can even use combinatorics to calculate this. Okay, how many such states there will be carrying a given quantum. There is another configuration which is a single D1 but wrapped twice. Okay, this is twice winding, so you go like this. It's not periodic. You can see the two ends are different, but then you continue and come and end here. So this is the same as this. A single D wrapped twice. So this counting has to be done separately. This is not a two-particle system. But this counting, in fact, is also obtained by in terms of the same C. So the result for this is C 8n minus j square. Okay, so let's see how we got 8n minus j square. So basically, the idea is that if it carries n units of momentum along S1, in terms of this D1 brane, right? The D1 brane effectively has twice the length of S1. So the unit of momentum on this twice wrapped D1 brane, okay, is half the unit of momentum on S1. So n units of momentum along S1 will correspond to 2n units of momentum on this D1 brane. But otherwise, the problem is the same. It's moving in the transverse space K3. Okay, so that's why you get this. So once you accept this, then the rest is straightforward. Okay, you just keep repeating this. So for example, for KD1 branes, we can have many combinations. So for example, we can have K single D1 branes, or 1D1 wrapped K times. And all possible combinations. Again, the counting is a little complicated, but if you are looking for partition function, then it's simple. So what I'll do is that I'll write down the expression for the final partition function, and I'll leave it as an exercise for you to check this. Okay, it's in fact the standard statistical mechanics of free Bose and Fermi gas. So ZD1, the final answer that we get is, okay, let me write this first. Q1 Nj, the definition, minus 1 to the 2j, d6 of Q1 Nj. Okay, but this is only for this d1, d5 side relative motion. Okay, that's what, and then e to the power 2 pi I Q1 rho plus n sigma plus j b. So this is given by the following expression. Okay. You see this C4n minus j square has become C of 4lk minus j square. That's because of the multiple winding. Okay. And this is the standard factor that you have for the Bose gas or the Fermi gas, right? For the Bose gas, it's 1 over 1 minus this. For the Fermi gas, normally you have 1 plus this in the numerator. Okay, but because of this trace is over minus 1 to the 2j, and there is a hidden minus 1 to the, sorry, this is minus 1 to the j, not 2j. Okay, because j already includes this factor of 2. Okay. And because this has this minus 1 to the 2h, okay, there's a minus sign in the numerator as well. So this I'll leave as an exercise. Are there questions? Okay, so now let's go to center of mass motion. So this is the motion of D1, D5 bound system inside KK, okay, basically at the center of KK. Okay. So you can think of again so D5 brane is wrapped on K3, okay, so it basically acts as, and K3 times S1, okay, and you are talking about, we are looking for states that in principle can carry momentum along S1. Okay. So this is again like a string, okay, moving inside inside this Taubner space. Okay. So this system has 4 transverse scalar degree of freedom. So this is again like a 1 plus 1 dimensional theory. Okay. It has 4 transverse scalars giving the position in Taubner. And it has also 4 fermions, which are the superpartners. Okay. And it requires a little bit of analysis to figure out what are the J and H quantum numbers of this. This is of course not hard because this is a vector of SO4. Okay. So the vector of SO4 carries both J and H. It's basically it's a half-half representation. Okay, so it carries both J and H quantum numbers. So it has both J and H. So this one will require some work, but basically one finds that the fermions carrying positive n, that's the BPA states, fermions carrying positive n, okay, that means positive momentum along S1, okay, they have J equal to 0, but H equal to half, or plus minus half.
Sorry, this 1 plus 1 dimension, in the one is the S1 tilde one, is that?
No, it's still S1 because this is wrapped on S1, right?
But it's
So
moving in S1 tilde, right?
Yeah, but it's at the center. So at the center, it looks like flat space.
Mhm.
Right? S1 tilde comes, see, S1 tilde is one of the angular directions.
Right, yes.
But this is at the, moving at the center. So it's still, you are just thinking of the 4-dimensional space as a flat 4-dimensional space in the transverse direction.
Okay.
So the underlying assumption is that the KK monopole size is much bigger than the S1. Okay, so the near the center, it's like almost flat space time. So because you are allowed to choose the moduli in any way you like, we can always take this configuration where the KK monopole size is much larger. That means S1 tilde radius you are taking to be much larger than the S1 radius. So the curvature of the Taubner space we are ignoring for this problem. Is that clear?
Can I ask
Yes,
another related question, which is you why can you just consider it to be a 1 + 1 dimensional theory with just the S1? Why isn't the K3 also there?
Yeah, so basically what, say D5 first of all is wrapping K3, right? And because K3 doesn't have a one cycle, okay, the D5 has gauge fields, of course, but the gauge fields don't do that. Okay, I'll not say that.
Sorry, you were cut off there. Could you repeat the last few seconds, please?
Yes, so the D5 is wrapping K3.
Mm-hmm.
So if K3 had a one cycle, then you could have said that the gauge fields that are living on the D1 brane could take, that could be Wilson lines associated with those one cycles. But because there is no one cycle in K3, the degrees of freedom associated with K3 are trivial. See, D1 brane motion in K3 have already taken into account, right?
Okay, yeah.
The D5 is wrapping the whole of K3.
Mm-hmm.
Is that point clear?
Okay, thank you.
Okay, so basically, okay, I mean, of course, you can always consider the gauge fields along K3 which are not BPS, right? I mean, because you are counting BPS states, you only look at the lowest energy excitation. Right? Otherwise, you can say, okay, you take the gauge fields in D5 and do a harmonic decomposition, right? Those will give excited states. Okay, but those are not what you are looking for. The lowest energy states basically have no excitations along K3 because D5 is wrapping on K3 and there are no massless modes in those associated with K3.
I think I'm still confused why the 1 + 1 dimensions, one of them is the S1 and not the S1 tilde, because I thought the D5 was wrapping both the K3 and the S1. So shouldn't its motion be an S1 tilde?
Okay, S1 tilde is in the transverse direction. So let me draw this. Yeah. So D5 is wrapping this direction. Okay, this is S1. Okay, let's ignore the K3. Let's assume that K3 is small, so you don't worry about this. So this is like a string. Okay? And this string is vibrating. Okay, in which direction is it vibrating? This is the direction of the Taubner space. Okay? So this is the 4-dimensional space in which it's vibrating. And S1 is part of this 4-dimensional space. In fact, near the center, S1 is just one of the S1 tilde is just one of the angular directions. So the world volume is 1 + 1 dimensional. It's moving the target space includes the S1 tilde, right? In particular, it includes the whole of Taubner space.
Right.
So it's one. So the when I say it's 1 + 1 dimensional, that one is S1.
Got it.
Okay. Any other question? Okay.
Yeah, actually, what you said in your earlier answer confused me because you said that there can't be any Wilson lines along the K3, of course, but what about Wilson lines along the S1 direction on the D branes?
Okay, yeah. So there could be Wilson lines along S1 direction, but okay, let me try to remember what happens. That those actually carry. Yeah, if I remember correctly, those will carry additional charge, and because you want to fix a charge, okay, we don't allow Wilson lines along S1 direction. But
I see.
I'll try to clarify this. I mean, we only allow momentum and not winding along S1 direction.
I guess they would carry a dissolved F1 string, maybe.
Exactly. Yeah.
Okay. Good.
And we are not allowing fundamental string. That will be different charge sector.
Great. Thanks.
Okay, let me then proceed. Okay, so I'll now write down the answer for this. So Z is given by product n equal to 1 to infinity. So this you will recognize is coming from the fermions. There is no V dependence because it's fermions, as I said, do not carry J charge. And these are from scalars. Okay, because minus sign clearly is a signal that these are bosons. And the scalars carry J charge, and that's why you see this V and minus V over here. Okay, so let me call this Z prime because you are not finished yet. Okay, there is something else that you have to do. Okay. So we still have to do, okay, we still need to consider the n equal to 0 mode. Okay, and this is what we are going to discuss next. So n equal to 0 mode are the modes that do not carry any momentum. Okay. So this is genuinely the center of mass. Okay, no oscillation at all. The whole thing, okay, as this one particle moving in tau naught. So this is like a super particle in tau naught. Just quantum mechanics. And we want to find the spectrum. Okay, and this one, in fact, was studied in a different context in the 70s, in fact. Okay, of course, not for this particular problem, but just as a mathematical problem of superparticle moving in tau naught. Okay. So I'll give the result. It turns out that the result depends on the sign of G45. Okay, so the spectrum changes as the sign changes. Okay. And this has to do with the walls of marginal stability, okay, that we discussed briefly earlier. Okay, at G45 equal to 0, this system is marginally stable. Okay. So G45, okay, for G45 positive, okay, let me give the result. So J here and the degeneracy here. All of these states have minus 1 to the power 2h plus j equal to 1. That means 2h plus j is always even. So you fill your h values accordingly. Okay. So j can take values 1, 2, 3, 4, etc. And the degeneracy goes as 1, 2, 3, 4, etc. Okay, so as you go to higher j, the degeneracy increases. Well, so you can calculate the partition function. Okay, so the partition function here is e to the 2 pi iv. So let me call it z double prime. That's a 0 mode partition function plus 2 e to the power 4 pi iv . Yeah, you can of course sum this. This is e to the 2 pi iv over 1 minus e to the 2 pi iv square. For G45 less than 0, we still have minus 1 to the power 2h plus j. 2h plus j equal to 1. But j now take negative values. Minus 1, minus 2, minus 3. And the degeneracies are 1, 2, 3, 4, etc. So the partition function in this case is e to the minus 2 pi iv plus 2. Okay, so the spectrum is genuinely different on the two sides. And that's what we expect. Across walls of marginal stability, the spectrum should jump. But what is peculiar about this is that these are actually the same functions. Okay, this function you can manipulate to write it like this. However, what it is saying is that they are, even though they are the same functions, here you have to expand in one way. Okay? You have to expand it in a way so that it converges for imaginary phi positive. And here you have to expand it in a way so that it converges for imaginary phi negative. And the reason that you get two different results by doing these two different expansions is because there's a pole at v equal to 0. So this is something we should keep in mind. Okay, that even though we'll write down one partition function, okay, they have different interpretation in different domains in the moduli space.
Sorry, last time you said that like the walls of marginal stability are ones which separate, like on one side you have half BPS states, whereas on the other side you have quarter BPS states. So is that still true? Like, is only one of these quarter BPS?
No, that's not what I said. What I said precisely is that as you go from one side to other, so on both sides you have quarter BPS state. But on one side you have that part of the quarter BPS state comes from a bound state of two half BPS states. Those go away on the other side.
I see.
But the bound state of two half BPS states is still quarter BPS. Okay, we are still counting quarter BPS states.
So did this have to happen this way, that you get the same function on both sides of the walls of marginal stability, or is it just an accident?
Yeah, well, at least it looks like an accident, but this accident happens in all the theories that are known. Okay, so there must be something deeper, but at least, I mean, certainly there is nothing in the calculation which would have told you beforehand that this had to happen this way. But the partition functions will remain unchanged as you cross the wall of marginal stability.
Okay. Interesting.
Okay, now finally, we have to do ZKK. So you have to take the product of the Z prime and Z double prime. Okay. So ZKK, I'll just write down the final answer, but the basic philosophy is the same. Okay. So the result for ZKK is this. Of course, you can do this counting by identifying its degrees of freedom, okay, as usual. Okay. But another simple way to arrive at this answer is to note that ZKK is actually dual to heterotic string theory, a fundamental heterotic string wrapped along the S1 direction. And that's what basically produces this partition function. This 24 comes from the fact that it has 24 left moving bosons, the fundamental heterotic string. But you can identify all of these 24 bosons also on the Kabachek-Klein monopole side. Okay, so you don't have to use this duality, but you can, the easiest way to get this answer is by using the duality. Okay. So now you basically have to take the product of all those. Okay, so let me write down the net result after you take the product. Okay. So Z rho sigma V is given by e to the minus 2 pi I rho plus sigma plus V, and then product J, K, L, N, there are integers, K, L, okay. So in fact, this part has exactly the same structure that you saw for the D1, D5 system, except the range has changed a little bit. So it's as if the role of the other two systems is to extend this product a little bit. Okay, again, it didn't have to happen this way, but this is what happens at the end.
Is there like any physical interpretation of that? Because I thought that like in the beginning when we wrote down that range, it was because you had to have like at least one D1 brane wrapping wrapping the S1 but you didn't have to have like multi-wrappings. So is there some way to interpret the new zero modes as like multi-wrappings or something?
No, we did use multi-wrapping, right? Because if you remember this, let's see where it went. This is multi-wrapping, right?
Right.
So it is included in this this part of the formula.
Right, but I thought that the K greater than 0, L greater than or equal to 0 range meant that, like, can I understand those as like the L is counting the number of multi-wrappings and the K is counting the number of individual D1 brains wrapping the
That's right, yeah.
D5?
Yeah.
So
Well,
then,
yeah. Okay.
now is there any way to interpret the fact that the range got expanded when you included the zero modes as something to do with the multi-wrappings? Does that make sense?
Well, see, this is more like having no D1 brain at all, right? The K equal to 0, right? Basically says that there is no D1 brain. Okay, KK monopole, for example, right, doesn't carry any D1 brain charge. Okay, the center of mass motion, right, that's insensitive to the number of D1 brains you have. So that's why what the rest of the contribution basically gave the K equal to 0 contribution.
Right.
Right? But why the coefficients that we get are precisely this, right? Is basically the C restricted to K equal to 0. That was certainly not guaranteed. It just happens that way.
I see.
Because this, I mean, you see that here, you had this force and so on, right? This 4 and 2. So these are basically the values of the C when K and L are 0.
I see.
Okay, that's how you could rewrite the final formula in this neat way.
Okay. Cool. Thank you.
Okay, so now the idea is that you can take this J. Okay, I should have said something else. Let me say this now. So this, in fact, is a famous function. This is written as 1 over phi 10 rho sigma V. Okay, this is what is called the Igusa class form. This is a modular form of weight 10. That's why this phi 10 of sp2z, which is a genus 2 modular. Modular space of genus 2 Riemann surface. Again, this symmetry is much larger than any symmetry that the theory itself has. And why it happens this way is still not well understood. But again, this happens for every n equal to 4 supersymmetric theories for which the counting has been done. Okay, that the symmetry group enhances to either sp2z or some subgroup of this sp2z. And you see that this phi 10 appears only after you have extended the product, right? Otherwise, it has no modular property at all. So even though we did the counting by thinking of this as 3 independent systems, each system has much less symmetry compared to what you get at the as a product, which has this full modular group of genus 2 Riemann surface. Okay, so now given that we know Z, we can expand it in powers of e to the power 2 pi I rho, e to the power 2 pi I v, and e to the power 2 pi I sigma to find B6 for a given set of charges, right? You just calculate the q square, p square, and q dot p and pick up appropriate powers of 2 pi I rho, 2 pi I v, and 2 pi I sigma, and read out the coefficient. Okay. So this in fact can be done by a computer program, right? Can be done on a computer. Everything is explicit, and you can actually get the numbers. But what we want, okay, at least for comparison to with black holes, for comparison to black holes, we need large charge expansion. Okay, not the values for individual Q and P, but how it behaves for large charge. And that requires a little more work. Okay. So let me explain how that is done. So let me write B6 as a Fourier expansion. Okay, so this is given by -1 to the power Q dot P. This is the -1 to the J that we had included. Okay. Integral d rho d sigma dv exponential -2 pi I rho p square by 2 plus sigma q square by 2 times z rho sigma. Okay, this is the one for phi 10. Now, one question that one can ask is that what is the integration contour? Okay, rho sigma and v you can think of as a complex variable. Okay, what of rho sigma v? So what integration contour we should use? Okay, so clearly because this is we are taking the Fourier transform, the real parts of rho sigma and v have to be integrated from 0 to 1. This has period. These are expansion in parts of e to the 2 pi I rho, 2 pi I v, and 2 pi I sigma. So real part of rho sigma and v run from 0 to 1. The question is what happens to the imaginary part? Okay. And here is what we'll use for the imaginary part. So imaginary rho, let's parameterize by C1 lambda, imaginary sigma, C2 lambda. In fact, C1 is not needed because it doesn't matter. Let me write this anyway. C3 light will make it more symmetric. Okay. So we take C1, C2 to be positive, C1, C2 larger than C3 squared, okay, and lambda positive and large. Okay, that's why you take the contour. Okay, so why this contour? Basically, you have to make sure. See these partition functions that we got. Okay, these we got by summing a series. Okay, so you have to make sure that we sum the series in a region of rho sigma v space where the series is convergent. Right? It's only in that region that you can trust this. Okay? And because this expansion is in parts of e to the 2 pi I rho, 2 pi I sigma, and 2 pi I v, okay? And L and sig k are always positive, as you can see. Okay? So it clearly converges for large imaginary sigma and large imaginary rho. For v, it's a little more complicated story. Okay? Nevertheless, what one can show is that if we restrict to this range, okay, so the expansion converges for these, okay, provided you choose some, there is something more about C3 that you have to say. Okay. But C1 and C2 should be positive because if C1 and C2 are positive, that means imaginary rho and imaginary sigma are large. Okay. So there at least it's clear that e to the 2 pi I rho and e to the 2 pi I sigma are both small in that region. Okay, so the expansion of Z makes sense. Okay. So let's take this for now, okay, and ask, okay, does it define this uniquely? Okay, does it depend on the choice of C3? C1 and C2 are positive. There is no ambiguity there. Okay, and again, this is needed. One can show for convergence. Okay, but then does this integral depend on the choice of C3? And how to answer this question is clear. So the answer is that as long as there are no poles, in this region, the result will be independent of the choice of C3. However, there are poles. And hence, the result does depend on C3. But this, in fact, has a very physical consequence, namely the different choice of C3 gives the result in different regions of M tau space separated by walls of marginal stability. So it's basically the same partition function that captures the results in different regions of M and tau. Okay. But you have to choose different contours. Okay, because as you move from one value of C3 to another value of C3, the contour passes through poles, the result jumps. But the new result represents the actual index in a different region of the moduli space. Okay. And this is the story, this is the generalization of the story that we saw earlier. Okay. That we saw earlier that we have this G45 positive and G45 negative, and the partition function is the same, but it depends on how you expand. Okay. That statement of it depends on how you expand, okay, you can also translate by saying that it depends on whether you choose the V contour to be imaginary in the positive region or the negative region. Okay. And those two give you the appropriate, actual V6 in these different domains, in the different regions in the G45 space. Is this point clear?
Yeah, and can we also see from here the point you made, I think like last lecture, that B6 should, although it changes across walls of marginal stability, it only changes in like an exponentially suppressed way?
Yeah, so here that comes in the following way. So you look at the jump is equal to the residue at the pole, right? And this one can calculate, because of course you know the function 1 over 510. And this turns out to go as exponential of charge, which is much smaller than the black hole entropy. Okay, we'll see how the black hole entropy arises here.
Thank you.
Okay, so let me now describe how the black hole entropy is calculated. So black hole entropy, well, maybe I shouldn't say black hole entropy right now. Okay, so calculation of B6 in a given chamber. In a given region in M tau space. Okay. So we fix our C1, C2, C3 and then start reducing lambda. Let me remind you the integral. So it has integral d rho d sigma dv e to the power 2 pi I p square by 2, sorry, minus p square by 2 rho minus q square by 2 sigma minus q dot p v times a rho sigma v. Okay. So when you take the imaginary rho, imaginary sigma, and imaginary v to be large, okay, say imaginary rho and imaginary sigma to be large, okay, then this I times minus I gives you a positive sign. So these are large exponents. Okay. So you start with a configuration where the integrand actually is large. But of course, the integral doesn't depend on the contour, right? So in the integral, there's a lot of cancellation, and finally you get things that is independent of lambda. So the result is independent of lambda. Okay, but the integrand starts reducing till we hit a pole. So the first pole we hit is at rho sigma minus b square plus v equal to 0. So now what we do is that we deform the contour through this after picking up the residue. One can show that the deformed contour gives contribution that are exponentially suppressed compared to the residue. So you can basically focus on the residue, okay, because this is exponentially suppressed contribution. Okay, if you want exponentially suppressed contribution to black hole entropy, of course you have to look at all this. But if you just want to first analyze the power law corrections, okay, then you can just focus on the residue. Okay. So let's see how we analyze this. So here you see already one variable is fixed. One of the three variables is fixed. By rho sigma minus b square plus v equal to 0 condition. And it turns out that the integration, the other two integrals can be done using steepest descent method. Other two integrals can be done using steepest descent. And this basically gives a fully systematic way, to get large charge expansion. Okay. So in principle, you can calculate B6 or log B6 to any power in 1 over charge. Okay, by doing this, because steepest descent method is well understood. This is just two-dimensional integral that you are trying to perform. Okay. So let me write down the result for the leading term and the next, the first sub-leading term. So log V6 turns out to be positive for large charge at least, is pi square root of p square minus q dot p square. You recognize this as a black hole entropy minus a function q dot p over p square. It's a function of two variables. I'll write down what this function is.
Ashok, you have about 5 minutes.
Okay, thank you. So this function is a complicated function. Okay, let me, here tau 1 and tau 2 just think of as a dummy argument. This is 12 log tau 2 plus 24 log eta tau 1 plus I tau 2 plus 24 log eta minus tau 1 plus I tau 2 plus, sorry, this is plus dot should come here. So plus dot. So this is ordered charge to the 0, and then there are 1 over charge square corrections. So eta is a dedekind function. Eta of tau is e to the 2 pi I tau by 24 product over n. Okay, this is a dedekind function. So everything is very explicit, and that's the complicated function you get. And now, of course, the question that you would like to ask is, up to this we have already seen, is this a Becker-Hawking entropy? Can we explain the correction? From the macroscopic side. So let me now tell you what we know about this, and then I'll stop. So this theory, heterotic on T6 or type 2 on K3 times T2, has a 4th derivative term in the action, 4th derivative term in the action of the following form. So let me write it as a delta S as 1 over 64 pi square integral So here this tau bar are the moduli fields that we introduced earlier. This phi is exactly the same function as this one. It's of course a completely different calculation, right? Here you are, this came from a counting, right? Here is just an effective action calculation. Okay, but the same function appears here. Okay, so this is a higher derivative correction to the effective action. Okay. Now we can ask, how does it affect the entropy? Affect the entropy. Okay. So for this, you have to understand what the higher derivative corrections do to black hole entropy. Okay. And this was in fact given by Wald, who of course was not working on string theory, but just wanted to see how higher derivative corrections look like. Okay. And he gave a very generic formula. So let me write this down. Okay. So I'm writing this down for spherical symmetric. But his formula is more general. So this is minus 8 pi integral over the horizon d theta d phi delta S delta R. This is the RT component of the Riemann tensor. Okay, that's the formula. You have to integrate this over the horizon. And this gives the usual Bekenstein-Hawking entropy for two derivative action. And one can show that the effect of delta S on S world is exactly the correction to log B6 that we found. So indeed, the microscopic formula seems to agree with the macroscopic formula after taking into account the higher derivative corrections to the entropy. But there is a caveat that I should mention, which is that in principle, this theory also has other 4 derivative corrections which could affect the entropy. There are some general arguments, but no rigorous proof that those corrections do not affect the entropy of supersymmetric black holes. So that's where things stand for this theory. So next time I'll discuss generalizations to other theories of this kind and of other kinds.
Sorry, this Wald formula follows from black hole thermodynamics, or?
Yeah, it follows from basically black hole thermodynamics.
Okay.
Okay, he asked that once you add higher derivative correction, how does the black hole thermodynamics change? And he got this general formula.
Okay, thanks.
So this side is purely macroscopic, right? There is no microscopic counting on this. I mean, he is certainly not thinking of microscopic formula. Okay. But once you combine this with Wald's formula, you find something that agrees with this log B6 that he counted from on the microscopic side.
Yes, thanks.
Okay, let's finish that and thank Ashok.
Thank you.
Let's take a few questions, but before we get there, there was actually a question in the chat from a while back that I missed. Let me, it's from someone whose microphone is not working very well. So it's from Aninda Banerjee. The question is, does this Taub-Knot supersymmetric quantum mechanics partition function have modular properties? So that was a while back.
Well, this by itself doesn't have modular property. I think this supersymmetric quantum mechanics was, go back there. Yeah, so this partition function by itself doesn't have modular property. But as you saw, after you include everything, okay, take the product of everything, then this has a big modular group, the sp2z, right, which is the genus 2 modular group. Does that answer your question?
Seems so.
Sorry,
yeah. He just responded. Yes, it does. Okay.
Okay.
Great.
Okay.
Okay. There are more questions?
Yeah. Can I ask a question?
Okay.
So you mentioned that when we are doing this analysis, we have to be aware of different chambers and when crossing through the walls of marginal stability. So how do you actually get the walls of marginal stability? Like, how do you know where in the moduli space they reside?
Yeah, so the way you know it, okay, maybe I can draw a figure, okay, that yeah, so basically the way you know it is that you equate the BPS mass QP to, this is MBPS, this time half BPS state you want, right? So say Q1, say AQ1, BQ1 plus M BPS of CQ2 DQ2. You see here I have taken AQ1, BQ1 and CQ2 DQ2 because these have to be parallel. These are half BPS. And then of course you have to have also Q, the charge conservation, AQ1 plus CQ2, and P is BQ1 plus DQ2. And then you look for all possible solutions to this equation, right? As you, for a given QP, you ask for what are the possible Q1, Q2, A, B, C, D that we can have, okay, for this. And then you solve this and see at which point in the moduli space this equation is satisfied. That's the way we determine the walls of marginal stability. Okay. And in fact, in this case, the wall of marginal stability is very well mapped. Okay, so let me say for fixed M in tau space. Okay, let me draw the walls first. So this is a complex tau space. So this is a real tau line. So this is 0, say. And so the walls basically look like this. This is 1. And then there are circles connecting these. And then there's a half minus half. So each chamber is basically circle enclosed by one circle, other 3 circles. Okay, so these you think of as generalized circles. Okay, going up to infinity. Okay. And basically what you can show is that given PQRS, all integers, such that PS minus QR is 0, there is a wall connecting P by R with Q by S. Okay, so these are all possible walls. You look for all integers satisfying this. So these are SL2Z matrices. Okay. Given an SL2Z matrix, you take this ratio P over R and Q over S. These are just rational points on the real axis, and there's a wall that connects them. Okay. If the point happens to be infinity, then this is straight lines. If the points are on the real axis, then these are circles. Okay. And the precise shape of the circles and straight lines, they depend on M. Okay, but it's completely known, and it's known by solving this formula that it should be marginally stable, right? So it should be possible to decay into a pair of half BPS states.
I see.
And
yeah,
and in each chamber you have some particular choice of C1, C2, C3 that tells you what the degeneracy, what the index is.
Yeah. Also, I had another question. So you mentioned that towards the end, we have to take the large charge expansion. Is that because we are dealing with black holes? That's why we want charge to be very large?
Yeah. I mean, we don't have to take it. On B6 has been computed. You can do it also for finite charges. But if you want to compare to the black hole entropy, right? The black hole entropy, the way it is calculated is by using supergravity and then the connections to supergravity, right? So supergravity action requires that the horizon size is large, the curvature at the horizon is large, is small, right? And that requires charges to be large.
Okay.
So
thank you.
From the black hole side, right, you only have a large charge expansion, right? This pi square root of q square p square minus q dot p square is the leading term, and then there is order charge to the 0 term, order charge to the -2 term, and so on. In fact, charge to the -2 terms have not been computed from the macroscopic side.
So following up on that, obviously you can't compare it to the black hole entropy if you don't take the charge to be large, but is there some interpretation of B6 that you get when you calculate it for small charge?
Yeah, it's just the index for that particular charge assignment. Right? It's a property of the theory. It gives the index for that charge.
Okay, but it won't have anything to do with like any kind of entropy or something.
Well, yeah, I mean, there have been attempts to give exact description of this. This is something maybe I'll try to describe tomorrow. Right? How to compute, at least how to develop the formalism to compute exact entropy from the black hole side. But right now, the techniques that are available is to take that exact expression and do an expansion in the large charge limit. Mm-hmm. But it requires doing a path integral. If you could do the path integral exactly, then you could get exact expression. And then you could compare the two sides. It's a question of what is the generalization of world entropy, which is exact. Right? World entropy is still not, well, okay, you can say in a sense, it's not perhaps exact, but it's if for any hard derivative correction, it tells you how to compute the entropy. Okay. But we'll see next time that that's not enough, because there are also logarithmic corrections to not this black hole and this class of black holes, but there are other class of black holes. For the world's formula doesn't work because the action becomes non-local. So those logarithmic corrections come from non-local action, okay, and the world's formula assumes a local action. But there are ways to deal with the logarithmic corrections as well. Okay, so we'll try to understand. So tomorrow's talk will be mainly from the macroscopic side. Okay. What is the systematic procedure for computing corrections to the black hole entropy? Okay, so that you can actually compare with these exact results that you have from the microscopic side.
Okay, let me suggest that we move together. And so let's thank Ashoke again.
Thank you.
And yeah, so I think probably continuing the discussion in Gather is a good idea.
Okay.
Okay. Thanks a lot.